Alrighty, welcome to the Mustang Math YouTube channel. I'm Jacob and I'll be discussing what these telescoping sums mean. They have a very nice name, but I'm not really sure what they mean, so let's figure it out together. So today we're going to go through some fundamentals first. So let's see what these fundamentals are. We have a sequences of numbers. So sequences are just a collection of numbers. As you can see here, we have some sequences. So this would be like, so you have this first number here, then you're adding 3 each time. And this one would be like a finite list since it's not going on forever and ever and ever. The second example starts at 1 and you add 1 each time. That's also a sequence, and that's infinite since these have these dots right here. That's what we try to use to signal that it's an infinite sequence of numbers. The third example, you start at 2, but you instead of adding numbers, you multiply 2 each time. So you get the next term, and that's also infinite, goes on forever using these 3 dots. Let's look at the next example. You start at 5, but you add 2 this time. And that also is infinite since these have these dots right here. So in general, sequences are finite as the first sequence right here, while other sequences are infinite, such as these right here. And we can kind of generalize the form. So we have like a finite sequence. Usually they have some ending point that is sometimes known. And infinite sequences, they don't really have a known ending point. So they go on forever. So a series is basically just the sum of the terms in a sequence. You take the sum of the numbers here, and you want to find that sum. You have this sum here, and you want to find that sum. Maybe this sum here, and you want to find that sum. I mean, the series is just a sum of the numbers in a sequence, and that's how you would find the problems would signal that you're trying to find a sum of numbers in a sequence. So So now we want to discuss what the telescoping sums are. And before we do that, we have different types of series that you'll see in math problems. So you have arithmetic sequences, geometric sequences, and telescoping sequences. So arithmetic sequences would be like 1, 3, 5, 7. They have a starting number, and the difference is always the same. So that's like what you see here, here, and here. But a geometric sequence, on the other hand, is different. You maybe start at 16, maybe go to 8, go to 4, go to 2, go to 1. So you're dividing by 2 each time. So there's a common ratio between 2 adjacent numbers. A telescoping sequence is a little bit different, and maybe you haven't seen it before. Arithmetic and geometric sequences are a lot more simpler, and you may have seen that before. So let's see what these telescoping sequences are. So in general, each term of a telescoping sequence can be expressed as a difference of another sequence. And this is helpful. So like, for example, you can have like AK equals BK minus BK plus 1. And you can plug this into each of the terms in this sequence right here, and you get something very easy to find out. And those are very easy to calculate. But I don't know, this notation might be a little bit difficult for you to understand. So let's go through an example of what a telescoping sequence looks like. So if we want to find the value of this sum, don't worry if you don't know about it. We basically just want to find this thing. So 1 over 1 times 2 plus 1 over 2 times 3, and so on until 1 over 10 times 11. So the sum, each of these numbers increase by 1 each time. And we want to find that sum. And the way we can do that is by noticing this. 1 over n times n plus 1 can be simplified into 1/2 minus 1 over n plus 1. That's because, you can just find the common denominator of n times n plus 1, subtract, and then you get this. And this is just, the numerator is 1, so it becomes something very nice. And this is very helpful because notice that they can all cancel out. These two cancel out, these two cancel out, and everything in the middle will cancel out. I don't have all the numbers listed out, but everything will cancel out. And so you just have these 2 n terms at the end. Those are pretty easy to figure out. 1 over 1 times minus 1 over 11, figure out that as 10 over 11. That's very helpful. So like for example, in this thing, you would have 1 over n plus 1 equals 1 over n minus 1 over n plus 1. So bk would be 1 over k. And ak would be 1 over k times k plus 1. Okay. So yeah, hopefully you understand and grasp the concept of telescoping sums, and let's look at a harder question. This is from the US AMTS, and it's a pretty challenging problem. There's nothing that comes to mind when you see this, right? So one trick I like to use is just set it as 1 plus 1 over x squared plus 1 over x plus 1 squared. You can notice that this is like the common term, okay? You can just, each term you're basically setting as this is x and then this is x plus 1. The two denominators here would kind of be consecutive. So let's see how this helps us. So you have x squared times x plus 1 squared plus x plus 1 squared plus x squared over x squared times x plus 1 squared. So we're trying to find the common denominator between these. And then this would want to try to simplify this. The denominator is very nice. It just becomes x times x plus 1. The numerator, on the other hand, is not as nice. So let's try to figure out what the numerator is. So this thing is x to the 4 plus 2x cubed plus x squared. And then the x plus 1 squared becomes x squared plus 2x plus 1. And then we have an x squared there. So x to the 4 plus 2x cubed plus 3x squared plus 2x plus 1. And then this thing is just x squared plus x plus 1 squared. That's very nice. And kind of just expand this here. And notice that this just becomes x to the 4 plus x cubed plus x squared. You have a x cubed plus x squared plus x squared plus x plus 1. This is 2, this is 3, this is 2. So it's a very nice factorization here, but it's kind of hard to see, but I'll give that to you. So x squared plus x plus 1 is a common term there. Okay, so now notice, we can try to simplify this now. I'm going to make this fraction a little smaller. Okay, perfect. So this would be 1 plus 1 over x times x plus 1. Okay, wait, I've seen this sum before though. Okay, so let's move this all here. Yeah, so we have this common term. Let's try to use that. So let's see. We have this thing and this thing. Okay, those two things are equal. So this would be like 1 plus 1 over 1 times 2, 1 plus 1 over 2 times 3, and so on until 1 plus 1 over 1999 times 2000. Okay, very long sum. Okay, let's notice that we can just use these ones. The ones, they all become 19999 since there's 19999 terms in total. Now we just have to find what 1 over 1 times 2 plus 1 over 2 times 3 plus and so on until 1 over 1999 times 2000. But this is kind of identical to what this was. Let's just apply what we saw there. So this would be like 1 over n times n plus 1 is the common term. We can separate that into 1 over n minus 1 over n plus 1. This is a very common term. Very common telescoping sequence that you'll see in math, so I recommend knowing that by heart. So this would be 1 over 1 minus 1 half when you plug in n equals 1. The second term would be 1 over 2 minus 1 over 3 when you plug in n equals 2. The third term is 1 over 3 times 4. 1 over 3 minus 1 over 4 when you plug in n equals 3. And so on until 1 over 1999 minus 1 over 2000 when you plug in n equals 19999. So we can cancel these all out. So everything cancels except the 1 over 1 minus 1 over 2000. This is 1999 over 2000. So we have something very nice that we just want to find. That is, well, I guess this is kind of already simplified already, but let's see, 1 over 1999 plus 1 over 2000, this is 1999 times 2000 over 1 over 2000. This is 2000 squared minus 1 over 2000. Yeah, so this is like 3999999 over 2000. Since this is 4000000. And yeah, so I guess this computation isn't too important, but this step is. So we're trying to use some telescoping sequence to try and find the result, and that's very important. This telescoping sequence you should know by heart, as I said earlier, and it's very helpful to know that. But yeah, I guess another trick we also applied is just instead of trying to figure out each number, each term of the sequence, and try to simplify that, instead we could just set this as x and this is x plus 1, and that can kind of simplify our calculations a little. So yeah. Now, one thing I want to just talk about here is products. They work very similar to what we've seen beforehand about sums. Yeah, so suppose we wanted to find like a product like this. We can write each term as this. So AK equals BK over BK plus 1. And just like the telescopic sums, these products simplify just as nicely, B1 over Bn plus 1. And so if we wanted to apply this example to this problem, notice that, well, these are like the BK is like the odd numbers, right? Like BK would equal 2K minus 1. And then we can cancel these all out. And we get 1 over 51. So just a very useful tip of these telescoping sums, and that everything cancels out and works out very nicely. So these are very cool in math. Hopefully you enjoyed this very fun lecture about telescopic sums and enjoyed these problems that we've seen, and see you next time.